So in this section, we are going to be considering our RLC circuits, which is an idea of a combination of a circuit which can consist of a resistor, an inductor, and a capacitor. So this combination can be in series, or it can be a combination which is in parallel, where we can have also a combined series parallel combination. So before we look into these in series parallel combination, we need to understand the properties of each component on its own. Meaning to say, working with a resistive circuit, a purely resistive circuit where we are dealing with only a resistor. What is it that happens in a purely resistive circuit? You will find out that in a purely resistive circuit, the current and the voltage are in phase. Remember, everything we are relating voltage and current. So in a purely, when it is a purely resistive circuit, all right? So in a purely, just gonna write in short, in a purely resistive circuit, current and voltage are in phase. That's the major part. Purely resistive, meaning to say, as you consider your circuit diagram, it is just a resistor that you have there, only connected to the AC. So that is the condition that you're going to be referring to. So this is current that will flow across the resistor. This is our resistor. So we can have further calculations from there, but the most important part is here. Then your waveform. Remember, these two, they are in what? In phase. So if you are to consider your waveform, you are going to notice that. All right, this is our reference, which is at 0 degrees. So they are all in phase, meaning to say, the only thing that is going to happen is the difference of the magnitude. But as we consider our waveforms, they're going to be exactly the same shape, exactly at the points where they cut or where they cross. This horizontal axis is going to be at the same points. Only the difference is going to be another one will be having what? A bigger value. As we consider, guys, in terms of the values, it is the voltage that has got a bigger value in terms of the magnitude. So the one that has got a bigger, that has got a higher value in terms of the peak peak values, there is the one for the voltage. Guys, we cannot have a circuit where a voltage maybe is 2 volts and the current is 30 amperes. Voltage will be bigger. Voltage is 240. Current maybe is 10 amps, right? So that is why we see this one of current being smaller. So this is for voltage, and this one is going to be for current, but they are in phase, like same points that we are going to be working with. So it is best that we have this in form of a vector diagram or a phasor diagram. So as we have our phasor or the vector diagram, it is best, because we are saying these two are in phase, it is best to understand that way in this form. So let's say this is our reference. We've got these two in at 0 degrees. So the voltage is going to be like this. All right. This will be your voltage. Current also in the same line. That is the consideration, guys, of being in phase. So this is the current that will flow or across the resistor. So you can call it IR here. All right. Or you can just write as current. As you can see, it is the same current that we have there. So that is what we are going to have, guys. Meaning to say, if the angle is 0 degrees, the presentation can be given. We can have this in the trigonometric way, all right, where we've got the maximum voltage, the sine of omega t plus what? Plus 0. So if there's a plus 0, it means there's nothing. It can be just given like this. It means there was a plus 0 there. There's nothing that is being what? There's nothing that is being added. So you can just leave it like this. Same with the current. So this is what? Purely resistive. So you need to understand your information, guys, what you're dealing with. So same part, let us quickly go to the inductor. We can have a condition of the inductors, a purely inductive. So in a purely inductive, you'll find out that this time current lags voltage by 90 degrees. All right. So in a pure inductive circuit, current lags voltage by what? By 90 degrees. That is the major part that we're going to have. All right. So just like the previous case, our circuit diagram, we're just going to have our inductor. All right. So this is it here, the AC, the current across the inductor. This is our inductor L here. All right. That's our voltage at a certain value of frequency. So if we relate this way, you are going to notice that on our waveform, it was supposed to be like this. Remember, our voltage is the major part that we work with. It is the major part that we actually relate to in reference. So it possesses the exact shape of the sine wave as it is originally. This is our voltage. But the current, it is lagging by 90 degrees. Meaning to say, if we were to consider, this is 0 degrees here, guys. This is at this point, this is 0 degrees. We're going to have 90 degrees, 180, 270, 360 degrees. Meaning to say, instead of us having a complete cycle completed like this in 360 degrees, we are not going to have it that way for this one that lags by 90 degrees. When it lags by 90 degrees, it means we were going to have the 0, this one. It was supposed to start here at minus 90 degrees. We were supposed to have this 0 here. Where we are having this 0 here, it was supposed to be at that point of minus 90. So it was supposed to start like this. It goes to the maximum value, just like this part, guys. Just like this, it goes to the maximum value. It goes back like this. That is how it was supposed to be like. But in this case, we cannot have two different starting points. So what happens is that for this lagging part, we're just going to take it as it is. We shift it. We move with it as it is like this. We move with it as it is like this, so that it can start at what? Also at 0. But now take note of this movement. It is not going to be a movement which is a straightforward movement like this, where it maintains this one. No. What it does is that we want to be careful of the points now that we're having. The point which is of this 0 here, this one, the 0 here, it is the minus 90. So in a normal consideration, is it going to be at this point of a 1 or it is going to be down? If you take it back to the 0. If you take it back to the 0, we are going to find out this one will be at a -1. All right, let me write it this way so that you can understand me here. Let us just say we have got sine. It was supposed to be just sine theta like this. But instead of being sine theta, you are now having a certain angle, all right, theta minus 90 degrees like this. Okay, so we want to start at 0 there. So it was supposed to be like this, 0. Instead of starting at minus 90 to say sine minus, we are not going to have it that way. We are going to maintain starting at 0 degrees. So if we are going to simplify this, it was going to be sine of 0 minus 90 degrees like this, which is going to give you a -1. So that is why I was saying this -90 that we see, when we push it back to be forced to start at 0, it means it is going to go back to the -1. So your graph now is going to be like this. Right, -1, somewhere there. We just want it to also cross this part. All right, also, or let me just redraw it. Let me just redraw it. So it is going to be like this. All right, at 90 degrees, that's where it is going to be at 0. Then it goes up. Remember, we must maintain the same shape of our sine wave. So we need to maintain the same shape. All right, it goes to the 270 like this. All right, then 360 like that, going like that. So it was supposed to be like this, actually. So like this. It was supposed to be like this. Going on like that. So that is the condition that you must work with. But in this case, we are just going to take it at this point where it is forced to start at what? At 0. So we're going to have this point at -1 if we are referring a condition which is direct at that point of 0 degrees, which will give us what? -1, which will give us -90. All right, so that is what we are going to have in this case. So we've got our voltage, and in this case, it's going to be current. So remember, current, just a smaller value compared to what? To the voltage. All right, so that's what you're going to have there. So guys, just know your graphs, guys, because these graphs, they're best when you just like you draw them, then you can explain from after drawing. So that'll be the best thing. And that issue, guys, of drawing and time does not correspond. So if you have something that is not on a mathematical view, then guys, anyways, I just hope you understood. This is your diagram at the end. So our vector or phasor diagram, in this case, we are going to have, like we said, current lags the voltage. So with our voltage on the reference here, remember the lagging part, this quadrant, the fourth quadrant. So if it is lagging by 90 degrees, it is directly on this line. All right, 90 degrees. That's a right angle. All right. So meaning to say our current is going to be directly going down. It lags. So this is the current that we're going to have, lagging by what? By 90 degrees. So that is what you're going to have, meaning to say if you consider a current under a purely inductive condition, it's going to be a certain current that you're given at an angle of what? -90. The current legs. Current legs. If we are given a certain consideration in terms of the current related to what? To the voltage, that will be negative. The voltage at what? At 0 degrees. The voltage is at 0. So using this, you can also consider for capacitors. So for capacitors, I'm just going to rush through since we already have for inductors. But here we just going to need, let's go back here. Do not forget your calculations, guys. You're dealing with an inductor, the calculations of the reactance XL. Remember, that's 2 pi FL. With the reactance, we can calculate the voltage drop across the inductor, which is our VL from the total current, as we do understand that this is the total current that we have. So it's just going to be total current times the reactance XL, where our reactance XL is at an angle of 90 degrees. This one, it is at an angle of 90 degrees. At an angle of 90 degrees when you write. Remember, it's a purely inductive part. The current is the one that lags, that carries a negative, but XL will be at a positive. So we're just going to look into questions. I think that will be best if we consider revisions of questions, if we work with the questions that can actually help. So you just need to go through the questions where the application of these formulas are to be used. So in this case, we need to consider another part. All right, I need, okay, there's something, all right, here. We need to consider the part of our capacitors, where the capacitors, where we consider a purely capacitive circuit. This time we are going to consider current. You're going to see current, it will lead the voltage by 90 degrees. So in a pure capacitive, circuit, we are going to notice that current leads voltage by what? 90 degrees. So that's the most important part. So consider your capacitor. It's just a pure capacitive. There's no resistor, there's nothing there. So the current, which is our total current, is actually the current across the capacitor. And we're going to have the voltage across the capacitor, this and that. So that is it. In terms of the waveform, we are going to notice that if this is our voltage, which is the part of our reference, and the current as it leads, we are going to be taking it from 0. This one will start at 1. So it will take the graph of a cos. So this one, from your mathematics, it will take the graph of a cosine. Like if you take this from 0 to 360, you can see this is the graph of what? Of a cos. So that is for what? For our current. Then the vector diagram, we are going to have it this way. In this way, the vector diagram or the phasor diagram. Vector or what? Or the phasor. With our voltage on the reference, I'm going to consider voltage on the reference, guys. So remember the current, it leads. This is the current of what? The capacitor. It leads by 90 degrees. To lead, you are supposed to be in the first quadrant, but we need up to 90 degrees there. So meaning to say we are going to have our IC this side, leading by what? 90 degrees. So that is the presentation that you can have in this case. Meaning to say it's current followed by an angle of 90 degrees. Phase angle is 90 degrees. So if you are to present your current, which is IC, it is supposed to be at an angle of what? Positive 90 degrees. So the idea there is to understand what you're dealing with. Just revise like what you're dealing with, waveform and this and that, and the calculations for XC, 1/2 pi FC, which also capacitance can be calculated from this. So that's our reactance, capacitive reactance in ohms. And with the reactance, the voltage across the capacitor can be calculated from the current times the reactance. So that's the total current times the reactance across what? Across the capacitor. That's it. So guys, do revise as many questions as you can. And also with this information, we can consider, like I said before, the circuits. The circuits, will see them. Okay, no problem. We'll see those circuits later on. Let us just see this one, the impedance, calculations of the impedance. But the impedance, guys, is best described when we are given resistance and reactance. Remember the impedance from R squared plus X squared. X is the reactance, which can be of the inductor. It can be of the capacitor. But in our part, guys, we are dealing with complex numbers. So the major part of us understanding the impedance is best based on the, it is best when based on the impedance triangle. The impedance triangle shows us a relationship which is between the impedance, resistance, and the reactance when they is a phase angle. So the resultant is our impedance, remember. So this part represent our impedance Z. The resistance on this side, and this will be our reactance. So here we are just considering a normal view. X can be like this. It can be a condition where we've got something like this in the negative. So it can be R minus JXC. It can be like this. We've got R plus. So this is just like a universal diagram. That's why we're just representing X as a universal value. We're not saying this is XL, this is XC. You will find out because of the sign that you have on your impedance to see if it is XC or XL. All right, so remember our phase angle here. So in order for us to represent this, Z as the phasor sum can be given as R plus JXL. So when we have got a positive, remember this one is going to be inductive, XL plus. So meaning to say a minus is when we are dealing with what? A capacitive reactance. A capacitive circuit. That's where we have got the reactance of the capacitor. We can have a condition where our impedance is actually equivalent to the resistance. In that case, it means we do not have any reactance to be added here. That will be a 0, which is a purely resistive circuit. The one that can be written in polar form as R. Our Z is going to be R angle of what? Of 0 degrees, to be at 0. A capacitive circuit is the one, when we simplify this in polar form, we're going to have the angle with a negative, a lagging angle, a lagging phase angle. Meaning to say, if we are given this, we know that it is going to affect our answer there. Whereas in this case of this one, we're going to have it in the form of R in the angle. It's going to be plus there. Plus in terms of the angle. So that is the conversions, guys, of your polar form and rectangular form. If you just take your calculator and prove 5 angle of 30 degrees, you'll see that is going to give you something like this. Maybe 5 angle of minus 30 is going to give you something like this. 5 angle of 0 degrees is going to give you something like this in rectangular form. So go through that and also revise your impedances in terms of the circuits. As an individual, I want you to go through your RLC circuits. If you are given a series circuit where we have got a resistor, an inductor, and a capacitor, knowing that we're going to have voltage drops which are different across the resistor, across the inductor, across the capacitor. The impedance, when it is to be calculated, R plus J XL minus XC. So you can use this part and compare from there. If you get a negative, then it means it's more capacitive. If you get a positive, it's more inductive. You just need to go on that part. And take a note when they give you a condition of a coil. A coil consists of a resistor and an inductor. So that's where we must have an RL circuit. You must have an RL circuit. That's the condition when you are dealing with what? When you are dealing with a coil. All right, let's just have this like this. So this is what you're going to have, guys. It will consist of a resistor and an inductor. So meaning to say, you consider the voltage drop on its as it is, the voltage drop of the coil from the total current that you are given or that you have calculated times the impedance of the coil. So where and how do we calculate that impedance of the coil? You find out the impedance of the coil. Since we have a resistor and an inductor, it's going to be R plus JXL. That's for the coil. So do revise, guys. Go through normal combinations of impedances when an impedance is taken into consideration in parallel. This is an impedance, this is an impedance. For us to find the total impedance in parallel, product over sum. All right, this is B, ZA times ZB over ZA plus ZB. Product over the product over sum. Remember that. The product is best done or simplified in what? In polar form. Whereas addition is best in what? In rectangular form. Revise all those series, parallel circuits. You must combine. The voltage drops, you already know, guys, how to calculate the voltage drop once there is a current and what? Impedance. You can have what? The voltage drop. So it can be from what? Current and reactances. That's it. So we are going to see typical examples, as many questions as we can from our textbooks, trying to figure out how do they ask question papers. So do not miss out any of the other classes that we are going to have. Make sure that you become part of the membership so that you have all the classes and requests under this subject and under other modules to be done under our engineering. That's it, guys. Till we meet again.